Dear students, welcome to the problem solving session on Milne Thomson's method part 5. In the previous videos, we learned the methodology and we solved few problems on Milne Thomson method. Either given a real part or an imaginary part, we know the steps to find the analytic function f of z. Just a quick recap, we did few problems on this kind. So either the real part is given or the imaginary part is given. We found the analytic function. Sometime if u is given, we found the analytic function f of z. From that, we found the complex conjugate v, either u to v or v to u. But now, suppose we want to find the analytic function f of z, but if the problem is like given 2u plus 2v, 3u plus 3v, or 2u minus 3v, 3u plus 2v. If you get mixed kind of u and v, how to solve it? There comes a question. We don't know which is the real part or which is the imaginary part, how to handle this problems. In today's session, we are going to deal these kind of problems. These are all some examples. We have to find the analytic function f of z given like 2u plus v is equal to e power x into cos y minus sin y. To deal these kind of problems, we need little basics. Suppose the given function f of z u plus iv is analytic. Now we take any real constants a and b, then I can form a complex number a plus ib. If I multiply this a plus ib with the analytic function f of z, I'll get another function. Let me take this as capital f of z. If this f of z is analytic, then this capital F of z is also analytic. Why? Because we have some results. Constant functions are analytic everywhere. Suppose you are taking 2 plus 3i, 3 minus 2i, etc. These constant functions are analytic everywhere. The next we have product of two analytic functions is also analytic. Suppose f of z is analytic and g of z is analytic. Then we multiply and we get a new function. I'll take it as h of z. If f of z and g of z is analytic and h of z is also analytic. So that is the reason if I am taking a plus ib, some constant function, it is analytic everywhere. And I am taking small f of z. This is also analytic according to the given question. Since both are analytic, when I multiply together, I'll get an output capital F of z. And this capital F of z is also analytic. Hope you understand, students. So this idea we are going to use and crack the problems like if you get 2u plus 3v, u minus v, etc. Suppose let us consider the given problem is 2u plus 3v equal to some function g of x comma y, and we have to find the analytic function f of z is equal to u plus iv. I will tell you two methods, whichever is suitable for you, you can pick. The given 2u plus 3v may be a real part of some other analytic function capital F of z, or it may be the imaginary part. So if you follow method 1, always we can convert this given problem as real part. If you follow method 2, always we convert the problem as imaginary part. Suppose you are converting this into real part, I will assume this as capital U, and for the imaginary part we will assume this as capital V. If we are going for the real part, then we write capital F of z is equal to capital Ux of x comma y minus I into capital Uy of x comma y. If you are going for the second one, here capital F dash of z is equal to capital Vy of x comma y plus I into capital Vx of x comma y. You can see how to remember this. Suppose you are remembering this formula for the real part, then it is very easy. We have Ux minus Iuy. When you go for imaginary part, just think it as opposite. So Ux means instead of u, put v. Instead of x, put y. So Vy. Then instead of minus, put plus. I into, for uy, I can write this as vx. Do you understand? Now we have to find the analytic function f of z. Just see the coefficient of u and v. The coefficient of u is 2. So let us take this as equation 1. Multiply 1 with 2. So now we get 2 into f of z is equal to 2u plus I into 2v. Next, see the coefficient of v. If the coefficient of v is plus 3, then we have to take minus 3i. If suppose the coefficient of v is minus 2, then you have to take plus 2i. So for u, you take the number as it is. For v, you have to multiply the number with minus I. This is the idea. So now minus 3i into f of z, that is equal to, we get minus 3iu, and then for the imaginary part minus 3i into minus iv. So we get minus 3 into I square v. We know that I square is minus 1. So minus 1 into 3 into minus 1 into v. So minus into minus plus, we get plus 3v. You can see the typed version. Now just add these two equations. Since f of z is common in the left hand side, I will take out. So we have 2 minus 3i into f of z. Here we have to club the real part and the imaginary part. So we get 2u plus 3v plus, I'll take this I in common, so we get 2v minus 3u. Therefore, we understand that 2u plus 3v is the real part of the function 2 minus 3i into f of z. Now, for problem solving, it is very tough for me to write like this. So I am going to assign this 2 minus 3i into small f of z is capital F of z, and 2u plus 3v as capital U plus I into 2v minus 3u is capital V. So we construct a new analytic function capital F of z is equal to capital U plus I into capital V. Why I say capital F of z is analytic? Because according to the question, small f of z is analytic. Constant functions are analytic everywhere. So multiplication of two analytic functions is always analytic. Therefore, 2 minus 3i into f of z is analytic. I am taking this as capital F of z. Hope you understand, students. If you get a question with a linear combination au plus bv is equal to some function phi of x comma y, where a and b are real constant, then using this method we will convert the given problem is the real part of some other analytic function capital F of z. So we can see the typed version. So I am assigning this as capital F of z is equal to capital U plus I into capital V, where capital F of z is capital U plus IV, U is small 2u plus 3v, V is 2v minus 3u. Now our given question is real part of this capital F of z. Now I will also explain the method 2, but I always prefer method 1 because whenever you have a linear combination like this, if you use method 1, always the problem is going to be real part u. For the method 2, as usual, we are assuming that f of z is analytic function, that is u plus iv. Now multiply equation 1 by coefficient of v. In method v, we multiply the coefficient of u. For method 2, first we have to take the coefficient of v and multiply with equation 1. 3 into 1 gives 3 into f of z is equal to 3u plus I into 3v. Next we have to take the coefficient of u and then just multiply with plus I. Here we multiplied with minus I. In method 2, we multiply with plus I. So 2i into 1, we get 2i into f of z. U into 2i is I into 2u, then 2i into iv. So 2i square v, that is minus 2v. Now we have to add this two equations. So when you add these two equations, we get 3 plus 2i. Here the real parts are 3u minus 2v, and then the imaginary part is 2u plus 3v. I am taking this I outside. Now you can see this 2u plus 3v is nothing but the given question. If you go by method 1, 2u plus 3 is the real part. If you go by method 2, this 2u plus 3v will become the imaginary part. So whatever the method you like, you can follow. I am going to follow the method 1. So whenever there is a linear combination, always I just take the coefficient of u multiply with f of z directly. And then I'll take the coefficient of v and multiply this coefficient of v with minus I in the equation f of z. When I add both, I will get this expression capital F of z is equal to capital U plus capital IV. And then my capital U is my quotient. So I always get the expression as real part.
Thanks for watching. Hope you found this video helpful. Subscribe to our channel and share it to your friends. See you in the next video. Bye bye.